Okay everyone, so we're going to continue with the equations of motions videos. In this case, we are going to start with this problem. As you can see, we have a skier on a ramp. So it shows that the design of the ski jump, as seen in the picture, requires the type of forces that will be exerted on the skier in her approximate trajectory. If in this case can be approximated by the parabola shown there, y equals 1 over 200 x squared minus 200, determine the normal force on the 150-pound skier the instant she arrives at the end of the jump at point A, where her velocity is 60 feet per second. Also, what is her acceleration at this point? All right, so we've done problems similar to this before in the normal tangential systems, but in this time we're asking about the forces and acceleration that we can have. So we're gonna do the equations of motions, but instead of doing it in the regular x and y, we're gonna be doing them in the normal and tangential directions. So let's write down the givens. We have the weight of the skier is 150 pounds. We have her velocity at A, which is 165 feet per second. We have also the trajectory, or the path of the curve, which is y equals 1 over 200 x squared minus 200. All right, that's the trajectory, and we are looking for what is the normal force at A, and also what is acceleration at A. Okay, so let's draw our free body diagram. So we're gonna have here our skier, right? There's gonna be going down the ramp. So down this ramp, we're gonna have our skier right here, and at point A, all right, we have the skier right here. So at A, what forces do we see? The only force that we have here is, of course, the weight. So mass times gravity, the weight of the skier. And at this point, because it's touching the ground, we have the normal force acting in the opposite direction. Okay, so we gotta define our coordinates. Notice, since we know this is a curved trajectory, we are given the path of the parabola. We know then the radius of curvature that he has. He has a radius of curvature over here of rho. So this instant that it is tangent to the path, we're gonna have here the trajectory in the tangential direction. And towards the center, we're going to have the normal direction, right? The normal direction. So those are going to be our directions for the equations of motion. So in this case, we're going to do the sum of forces in the normal direction, with up being positive, and this is equals to mass times acceleration in the normal. Acceleration in the normal. So let's see, what forces do we have in the normal direction? Well, we have normal force at A minus the weight, and this equals to mass times acceleration in the normal. So out of here, we can rearrange. And so for that, normal force at A is equals to the mass of the skier. So that will be 150 pounds divided by 32.2 feet per second square. And this is multiplied times the normal acceleration, right? Where we can figure this out, right? We can keep it as an, or we'll see. We'll keep it as am for now, and this will be plus the weight, which is 150 pounds. So we need to figure out the normal acceleration so that we can find the NA right here. All right, so we know once again at A, the normal acceleration that it is happening, right? We know acceleration in the normal direction, it's equals to v squared over rho. We do know her velocity at A. The velocity at A is it's given, and we also have what's it called? Well, we do not have the radius of curvature. but we're given the trajectory. So just like we did before, we can figure out the radius of curvature with the equation of 1 plus the derivative of the trajectory function, square everything here to the 3/2 and everything divided by the second derivative of the trajectory path, the absolute value of it. So let's derive then our path. So the first derivative with respect to x of 1 over 200x squared minus 200, this will be 2 over 200x, or 1 over 100x. And if we take the second derivative of this, or the derivative of the derivative, right, this will be equals to 1 over 100. So all of that, if we plug it in and we evaluate it here at x equals 0, right? Because let's imagine that this at a is our 0 in the x and y coordinates. So yeah, so if you evaluate the radius of curvature at x equals 0, notice this term will go away. Out of it will just be a 1 divided by 1 over 100. So we end up with 100 feet for our radius of curvature. So in this one, with these values, we can now find the normal acceleration. So over here, so normal acceleration will be 65 feet per second, everything square, divided by 100 feet, which will give us approximately 42.25 feet per second square. And that is the acceleration at that point. Plugging that in, we're gonna then find, right, if we plug that into the equation right here, we're gonna find the normal force at A, it's equals to 347 pounds.